This is going to be section 3, 7, day 1. And so this section is about implicit differentiation. And so you know that this entire chapter 3 has been on different strategies for differentiating. And so implicit is kind of adding to that repertoire of strategies. So the question for today is, when is implicit differentiation used instead of regular differentiation? So in order to kind of figure that out, we have to talk about what implicit means. So I want to start off by talking about the word explicit. Explicit, here are some synonyms for explicit: accurate, categorical, certain, clear, correct, definite, definitive, exact. I've starred precise, exclusive, and direct. I think I probably like the synonym exclusive the best. I think in the math sense, it best explains what explicit expressions are. So in the area of math, explicit expressions look like these. And if you notice these three expressions, the first thing you might notice is that they're all functions. The second thing is that you might notice is that they can be easily solved for y, or in other words, we can write them in terms of y equals, or f of x equals is basically just saying y equals. Same with g of x equals. So you can easily solve them for y equals. That's a big characteristic of an explicit expression, and that they're functions. And so now that we've kind of categorized what explicit expressions are, since implicit is an antonym, we can look at then the antonym for explicit, or in other words, we're looking at implicit. Here it is. It's an antonym for that. So since it means the opposite, then we have to take a look at these expressions. These are now implicit expressions. And if you notice, this one can be easily solved for y. And in fact, this one can as well. The top one is a line. The next one is a circle. But when we solve for y here, we bring the x squared to the other side. We'd square root and get a plus or minus. We end up getting two separate equations. So leaving it in its implicit form is actually more advantageous. And then these last two, we definitely can't solve for y. There's just no way we can easily isolate the y's in these expressions. And so some of the characteristics you might see then is it's increasingly more difficult to solve for y. Just can't be done easily. And then the other thing that you might notice is that many of these are not functions. This is the only function as the top one. Even though we can write lines implicitly, we call that standard form in algebra. This is a circle. The next one down here is a hyperbola. And then I have no idea what this is, but it's got to be wavy like a sine function. And it probably has some quadratic qualities too, like a parabola. The prospect of these actually being functions is getting slimmer and slimmer. So these are our implicit expressions. And so the question is, well, how do we differentiate these? How do we do a dy dx per se when we can't solve for y? So that's kind of the major answer to the question of when you need implicit differentiation, is when solving for y is difficult. So as we look at, and this isn't in your notes, so this is kind of just a short discussion about differentiation and what we've been kind of doing and what it really means up until now. For instance, every derivative problem we have can be thought of as a chain rule problem. And we kind of went through this in an earlier discussion. Let's go back to x squared. So if we take the derivative of the function x squared with respect to x, that means since we're taking the derivative with respect to the variable x, that's what the bottom of this Leibniz notation means, then we have to come back up here and we have to decide, okay, x squared is a polynomial function, so we need to do the power rule. And we need to do the power rule on this variable x. So as you might guess, then, this derivative is just 2x. Well, let's kind of see where that comes from. If we think of it as the chain rule, we can think of maybe brackets around the x, where the outside function is, the inside function is x, and the outside function is x, is something squared, or that stuff in the bracket squared. So if we do a chain rule on this, here's the derivative of the outside, 2x, and then the derivative of the inside, d dx, in other words, the derivative of function x with respect to x, is just 1. So this ends up being 2x times 1, which is just 2x. So, you know, we've been kind of glossing over the fact that it's really, I think, pretty easy for most people to look at this question, what is the derivative of x squared with respect to x, and come up with the answer, 2x. This is really what's happening in between, is they're doing a chain rule. It's just that this d dx of x is just a value of 1, so it tends to kind of get dropped off. But this in process is really important when we talk about implicit differentiation, because now what's happening is this term or this expression right here that I'm kind of hovering around is no longer written in terms of x, it's written in terms of y. So for instance, and that makes the chain rule very necessary. So for instance, let's try taking the derivative of y squared, but we're taking it with respect to the variable x. So there's a mismatch here. If this down here, if we were taking the derivative of y squared with respect to y, it would just be 2y, just like this is 2x. And that's kind of where we start. We say, well, let's do the power rule on y. So we end up 2y. And then with the chain rule, the inside here, we have the derivative of y with respect to x, or what we call dy dx. We don't know what dy dx is. So it's not 1 like dx over dx is, but it's something else. So the idea then is when we're taking the derivative of a variable that doesn't match up with what's in the bottom here, in other words, with respect to yet another variable, we have to have this chain rule on the end. So the outside function, that's that derivative, 2y. This is the inside function, dy dx. And so that derivative then is just 2y dy dx. And that's how we take the derivative of functions that are not in terms of x. And like I said, with implicit differentiation, this is really necessary, because our strategy here is going to be to do derivatives on every term in the expression from left to right, from the left side of the expression to the right side of the expression. So here is kind of the process that you can get down into your notes. We're going to differentiate both sides, and we're going to differentiate them with respect to x, which means everything that's not in terms of x is going to have to be differentiated with the chain rule. And that's going to leave us with a lot of dy dx expressions. So every time we differentiate a y term, we're going to have a dy dx on the end. So we're going to have one or maybe several dy dx terms. And so we're going to collect them on one side, and then we're going to factor out the dy dx term, and then we're going to solve for it. So really, everything beyond step 1 is algebra. Step 1 is the calculus, differentiate. Steps 2, 3, and 4 are algebra. So let's try this with something that we're really familiar with. For instance, let's do the derivative of x squared. We kind of go back to x squared a lot. You know, it's just this basic parabola, but we get a lot of mileage out of it. So if I ask you what the derivative of y with respect to x is, you're going to say it's 2x again. And interestingly enough, if we step through the steps, so I'm asking you to find the derivative of y with respect to x, so I'm going to write the derivative of y with respect to x equals 2x. And in doing this step, the way I have it written, I've actually differentiated this implicitly. On the left-hand side is the variable y. I took its derivative, which is 1, but then I followed it up with a chain rule, dy dx. And so this is actually the implicit derivative of y. And then on the right-hand side, we just had variable x, so we just do the plain old power rule like we know how to do. So you've been doing the implicit differentiation all along, you just haven't been really calling it as such. So let's try something a little more advanced. Let's try finding the derivative of y squared equals x squared. So we could still solve for x in this expression, but it would give us two equations kind of like the circle. If we square rooted both sides, we would have the square root of y equals plus or minus the square root of x squared. So if you think about that, the plus square root of x squared gives you the top portion of this relationship, and then the negative square root of x squared gives you the bottom portion of this expression, or the bottom part of the v. So let's take the derivative here. So on the left-hand side, we have to do it implicitly since it's a variable y. So when we take the derivative of y squared, we do the normal power rule, 2y, and follow it up with a dy dx. Equals, and then we do the derivative of the right side with our normal power rule, and since it's an x term, we just do our normal derivatives. So that derivative of x squared is 2x. Okay, so we've differentiated. We've done step 1. Now we're going to collect the terms with dy dx on one side. Well, the terms with dy dx are already on the left, so we really don't even have to do step 2 in this case. Which means we don't have to do step 3 either. If there's no collecting, there's no factoring. So we're down here at step 4, where we solve for dy dx, which means we have to divide out the 2y. So we divide out each side by 2y, and we get this expression. So there's the expression for the derivative. And if I simplify that, I get x over y. And so if you notice, we started out with an implicit form for an expression. We ended up with an implicit form for a derivative, which hopefully makes sense. If you start out with an implicit equation, you're going to end up with an implicit derivative. And all that means is that if I wanted you to talk about the slope, remember slope is a number, I would have to give you the x and the y coordinate so that you could find the slope. For instance, let's talk about this point 1, 1, right there in the first quadrant. Okay. If I plug 1, 1 into the derivative expression, I get 1 divided by 1, which is 1. So if you think about being at that point right there, the slope of that line is 1, which is the derivative. Let's take over 2 up 2. Okay, so x coordinate of 2, y coordinate of 2. Right here, my slope of my function, or my slope of my expression is 1. Excuse me, 2 divided by 2 is 1. Let's take a look like over here in the second quadrant. Let's go left 2, up 2. So that's negative 2, 2. So if I put in negative 2 for the top, 2 for the bottom, that's negative 1. And if I go right here on my relationship, on my expression, the slope of my expression, the derivative of my expression, is negative 1 there. So if you notice, you've got to have both the x and the y coordinate to find the slope. So let's move on to some a little more complicated expressions. This definitely can't be solved for y. This is one of the ones that we started out the discussion with. And so this is where the implicit method comes in handy, because we don't have to solve for y. We can just collect our dy dx terms after we've done the derivative. So we're going to have to start differentiating from left to right. So we're going to take a derivative of this first term. So we're taking the derivative of 2y with respect to x, which means we're going to do the power rule on 2y, and then we're going to follow it up with a dy dx. And then that equals, and then we're going to take the derivative of the next term. The derivative of x squared with respect to x is just our straight power rule, because these two variables match. And then we have to take the derivative of the sine of y. So again, we're going to take the derivative. Now, we have to use what we know about trig functions and derivatives. So we have to take a derivative of sine with respect to y, but then we have to follow it up with a dy dx. Okay, so let's try this. So the derivative of 2y is just 2 if it's with respect to y. So this first term then is going to be 2 dy dx. And then this next term, the derivative is just going to be 2x, just your regular old power rule, because it's the derivative of an x term with respect to x. And then this last term, the derivative of sine is cosine. So the derivative of sine of y is cosine y. But then since it's a y term, we need a dy dx chain rule. So there's my derivative. So I've gotten through step 1 of my process. Now step 2 says collect the the dy dx terms. I'm going to move this cosine y dy dx to the left-hand side. And so if I do that, that means I'm subtracting cosine y dy dx from both sides. So it looks like this, 2 dy dx minus cosine y dy dx equals 2x. So now that I've collected all my dy dx terms over here on the left, I can factor out a dy dx. So if I remove these from each term, then what's left is the 2 minus cosine y in the brackets. And that equals 2x. So now I can go ahead and divide out the 2 minus cosine y and finally isolate dy dx. So as you can see that from this point down is all algebra. So my derivative is 2x over the quantity 2 minus cosine y. And so I still need the x and the y coordinate on this function if I want to find the slope at a certain point. So let's go ahead and try that. Let's find the slope when x is 3 and y is 4.1 radians. So we're going to put a 3 in for x. We're going to put a 4.1 in for y. Remember, that's radians. So this is just a little bit bigger than pi. Here's what this looks like. Remember, we kind of talked about its characteristics. It's wavy like a sine. It might have some parabolic or quadratic characteristics. So this kind of looks like a wavy parabola. So we're going to be over 3 and up 4.1. There's the point we're at. When I put in 3 and 4.1 and make sure I'm in radian mode, I get 2.33. So my tangent line here has a slope of 2.33. And then if I know my slope and I know my point, just like the posters we've been working on these last few days, I can write the equation for my line. 2.33 times the quantity x minus 3 plus 4.1. So that's the slope of that, that's the equation for that tangent line. Let's talk about that circle. Here's a circle that has a center of 0, 0 with a radius of 5. It's not a function. And so our best bet is to, instead of solving for this and introducing a radical, we're going to use implicit differentiation. So to set this up, we're just kind of acknowledging that I'm taking the derivative of an x squared term with respect to x. Then I need to take a derivative of a y squared term with respect to x, so I'll need a chain rule there. And then I have to take a derivative of 25, which is a constant, with respect to x. So let's start with this x squared here. So derivative of x squared with respect to x, those variables match up. Our straight product rule tells us that's 2x. Okay? Let's take a derivative of y squared with respect to variable x. So we have a mismatch there. So we do the regular power rule, 2y, and then followed by the chain rule, dy dx, to get that in the terms of the right variable. And then the last derivative we have to do is on the right-hand side. And this is a constant, and of course we know that constants have 0 slope. So the derivative of 25 must be 0. So we have our chain rule here. Just kind of noted it there. We've differentiated. That was our step 1 in the process. Collecting our dy dx's, we only have 1. So we can go ahead then and we have 1 dy dx. There's no factoring involved. And so I can go ahead and move the 2x to the right-hand side by subtracting it. And then I can divide by the 2y. And I can simplify this if you want to, but you don't have to. But if you simplify this and cancel out the 2's, you have negative x over y. So there's our derivative for our circle. So if you think about this, let's say we're over here in the first quadrant, up here in this picture of a circle. X and y are both positive. So let's say we're right here. And if x and y are both positive, then we have a negative slope. So if you think about it, your tangent lines in the first quadrant are slope downward or slope negative. Let's go over here to the second quadrant. We have a negative x and a positive y. So a negative x and a positive y would make this opposite of a negative, which is positive. So if we look at the tangent line over here, we've got positive slope or positive derivatives. And we could do, reason the same for the other two quadrants. Third quadrant, they're both negative. So a negative over a negative is a positive, but then we have a negative up front, so we have negative slope here, and so on. So specifically, let's talk about the point 3, 4. So over 3 up 4, that makes a 3, 4, 5 right triangle. So I want to know what the slope of the line tangent to the circle at that point is. So I'm going to go ahead and put 3 in for x and 4 in for y. And our slope is negative 3/4. So the slope of this tangent line is negative 3/4. If I wanted to then write the equation for that tangent line, since I have the slope and a point, I can put it into the point slope form. So I have a slope of negative 3/4. I have a point of 3, 4. I'm going to put it into here. So we're going to have negative 3/4 for the slope, x minus 3, because that's our x coordinate, plus 4, which is our y coordinate. And then once we have the slope point form, it's a really quick switch to get to our normal line. So here's our tangent line. And then our normal line, all we do is take the opposite reciprocal slope. So all we're doing is we're coming to this expression, looking here at the slope value, flipping it, and taking the opposite sign. So if you look, there it is. Everything else stays the same because we're still going through this point. So all I did is opposite reciprocal, make my slope 4/3, and then that would be my normal line right here. So now I have a tangent line and a normal line at that point. And I found the derivatives or the slopes of that using implicit differentiation. So at this point you can start your homework. It's implicit differentiation. It's actually day 1. That's a typo.